Okay, so we are moving along in chapter two. We are going to be talking a little bit about how we picture molecules and how we name them, and then we're going to talk about the main pollutants that we're concerned with in the atmosphere. I'm also going to spend a little bit of time talking about scientific studies in general, just so we have some terminology and some ideas of what scientists think about credibility. And that's a theme we'll come back to periodically throughout the semester. So I would like you to read the end of the chapter 211 through 216 for Thursday. We won't get through all of it on Thursday, but we will have a quiz next Tuesday. So that's basically going to be about chapter two. I do expect you to still be able to find things on the periodic table. So kind of talked about that in chapter one. That's going to be something you still need to be able to do throughout the semester. So keep that in mind. So questions? All right. All right. Okay. So you probably noticed that you have on your desk some little models. And so we are going to try and figure out the formulas for these models. So there are different kinds of formulas. The one we're concerned about is the molecular formula. And a molecular formula shows what are the elements and how many there are. This up real quick. On the models that you have, anything that is black is a carbon, anything that is white is a hydrogen, red is oxygen. This is blue. I know it's kind of hard to tell. It looks almost black. Sulfur is yellow, and then you do have some green ones. Green is chlorine, so I'll write that over here. So what we would do, you all should have something that looks like this. It might have longer bonds, but it should have a red and two whites. So what are the elements in here? Oxygen and hydrogen. So we would say that this is O for oxygen, H for hydrogen, and then we would put numbers to tell how many there are. Don't write the number one. Ones are invisible in chemistry, so we're just going to leave the O the way it is, and we can put a 2 after the hydrogen. So there is a logic to the order that chemists put it in, but for right now, I just want to get the names of the element or the symbols of the elements and their numbers down. So how would we normally write this formula? H2O. So this is water, right? All right, so you feel like you know what the formulas are? You need a couple more minutes. Okay, let's take a look at these. All right, so this one has a light blue with 3 whites. What formula would you say that is? So that's the name. What's the formula? NH3 is the formula. And then I am going to get to the names. So we'll put a pin in that for just a moment. Okay. What about this one? CO. That's going to be one of our important pollutants. Okay. What about this one with the 2 greens? Cl2. Okay. And let's see. I don't have the long one that has the blacks and the whites. So here, let me borrow this one to hold up. Okay. So this one, its name is alanine. We're not going to name this the way we name normal things, but what is this? Or what is the formula? C3H4. Very good. That goes through all of them. Okay. Let's see. That one. Okay. And then, okay. So I didn't have enough to make these. What would this one be? CO2. Okay, so we had one that was just CO, one that's CO2. Okay. And what would this one be? O2. Okay. So one thing I want to point out is that there are several elements that form what we call diatomic molecules. So two atoms are in the molecules. Okay. There's our diatomics. The other thing that we talked about on Thursday was naming our binary compounds. So binary means there's two elements. So these all have two elements in them. And so remember the first element in the name, we just say the name. Okay? The second element, we have to change the ending to I. Okay, so think about ones that you know. What's the name of this one? Carbon dioxide. So you know that one. That'll help you remember everything ends in I. Okay. Then we use prefixes, and I will have a list of prefixes on both your quiz and test. Actually, for the quiz, I'll probably put it on the board, but I'll have it on the front cover of the test because I know not everybody happens to know hepta or 7 off the top of their head. Tetra means 4. You've heard of the game Tetris with the blocks that kind of fall down into place. Each of those blocks consists of 4 squares. So that's why they call it Tetris. Okay, so water, we have a common name for. We also have a common name for this one. I'll get to that. But we could name this by its formula here. So how would we name that according to what we call the systematic rules? So we have a 2. What's that going to be? Di. And then the first element, we just write the name. So what's the element? Hydrogen. And then what do we say for 1? Mono. Well, we don't want to put 2 O's next to each other. So we just say monoxide. Okay, so that's that one there. We always use mono for the second element. I didn't make up the rules, that's all I know. Mono gets left out for the first one. You might remember that one. So if I'm looking at this one, which is also ammonia, you may have heard of ammonia is used in cleaners and things like that. But for this one, instead of saying mononitrogen, we just say nitrogen. We leave the mono off. So it would be nitrogen 1. What do you think 3 might be? Tri, like tricycle. Okay. Trioxide? No. What's the element? Trihydride. There we go. And then we already said this one was carbon dioxide. This one would then be what? Carbon monoxide. Okay, some other things we're going to be looking at later. SO2. What would that one be? Sulfur dioxide. So sulfur and nitrogen come in a couple of different versions. So this one is sulfur dioxide. We can also have sulfur trioxide. Both of those pollutants kind of come from the same place. Your book mostly focuses on dioxide though. Nitrogen comes in lots of varieties. So this is one of our chemical laws called the law of multiple proportions. And it says that two elements like nitrogen and oxygen can combine in lots of different ratios. There'll always be these nice whole number ratios, but they can combine in lots of different ways, but they'll be different chemicals. So here are some of the chemicals that nitrogen can form with oxygen. See if you can name those. Just kind of go through the list. Don't need to say them out loud just yet. Now for these two, we only have one nitrogen, so we're not going to use mono. We're just going to start with nitrogen. So the top one is nitrogen monoxide. And the next one is nitrogen dioxide. So this one is very commonly found in pollutants in smog. It has kind of an orangey color to it. This one can also be formed similarly, but it's actually used in some different kinds of medications. So it can be important medically as well. And so this kind of emphasizes one of the points I like to make in this class. Chemicals are neither good nor bad. They have some beneficial things and they have some harmful things that can happen. And sometimes the same chemical can do both. And this is a good example of one that is important in medicine, but it's also harmful if we just breathe it in. Okay, this one looks very similar to this one, but how is it named differently? Dinitrogen monoxide. So while this one we don't, or I'm sorry, this one we said is that orange chemical, it's hard to breathe. You don't want to breathe that one. This one also goes by the name of nitrous oxide. If you go to the dentist and they put a gas mask on while you have a filling done, I know you all have perfect teeth, you never had a filling. I have lots of cavities. They used to use that. That's what this is. This is dinitrogen monoxide. It's also used as a fuel additive because it has a higher ratio of oxygen than the natural air does. So what is the percent of nitrogen in our normal air? In this room, what's the percent? That's one you got to know. 78, okay? So in the atmosphere, N2 is 78%, and O2 is 21. But if I have this and it rearranges itself to form those two chemicals, the ratio of nitrogen to oxygen is, there are two of these, 2 out of 3 is what? 67%. And the O2 would be 33%. Okay, so you use that in order to increase the oxygen that's available for an engine to run, because instead of the air being 21%, now you have 33%. Okay? If you are somebody who likes whipped cream on your pies and desserts and things, Thanksgiving, you put whipped cream on it and you have one of those things, you push down the button and it shoots out the whipped cream, the gas that they use to fill out the foamy places in there, that's also nitrogen, dinitrogen monoxide. So that one has lots of fun uses. Okay, and then finally this one, dinitrogen pentoxide. So I usually say pentaoxide, but technically you're supposed to drop the A. So collectively, because all of these can be made with the nitrogen and oxygen in the air, collectively these are known as NOx. Okay, so when we start talking about pollutants, we'll talk about those as NOx. Okay, one other pollutant we're going to talk about later is not a not a binary. It doesn't have two different chemicals in it the way these and the carbon monoxide does, but it's not the normal form of the element. So oxygen normally forms O2. But it has different allotropes. So we talked about this way back at the beginning of the semester with carbon. I held up the models that are over there by the whiteboard, where we have diamond as a kind of carbon and graphite as a kind of carbon. Well, oxygen has two forms. One of them that it makes up almost all of the normal oxygen is just O2, so it's a diatomic. A much less stable form is O3. This. And this is ozone. Okay, so they're both made of oxygen atoms. This is a different allotrope. Okay, so those are the pollutants that we'll end up focusing on. All right, let's see where I am. Okay. Any questions about any of this stuff? We're not going to dive into the pollutants just yet, so I want to make sure I get through the other things. Okay. Okay. First of all, I do a lot of things well. Spelling is not one of them. Feel free to point out my mistakes. I'm always open to learning how to spell things, but you will notice spelling errors. Sometimes I will ask you. Okay. So with scientific studies, I know everybody's had in a class, this is the scientific method, and we start with the problem, and then we have a hypothesis, and then we have a procedure, and then we draw conclusions. Slight variations along the way. Maybe you throw in results or a discussion or whatever. Some things, so I'm just going to kind of point out some things that I think are important that may or may not have come up. Okay, so one important thing is science investigates the natural world. As opposed to supernatural. So this is a really misunderstood concept. And even a lot of scientists kind of lean on the side of the popular view of this. Science really doesn't have anything to say about the supernatural world because we can't investigate it the way that we normally would. So when we talk about supernatural, of course, you might think of things like ghosts or paranormal phenomena, but also included in there might be things like astrology and energy crystals and religion. It's not that science says that those things aren't real. That's not the issue at all. It's just that science can't investigate them because science has to have a testable hypothesis. So if we look at something like, say, even a big picture like the existence of God, because God is presumably omnipotent, all powerful, can do all things, there's no way that we can have a test that there isn't the argument, but it's possible that God did X, right? So we can't really test the existence of God. That's just not possible. So some scientists are kind of like, I'm all in on science, and so therefore I can't believe in religion. That's not really the case for science as a general rule. Science just doesn't have a lot to say about religion because it can't deal with it. You know, it's kind of like me talking about economics. I know a little bit about economics, but I can't teach you economics. I don't have a lot to say about it. That doesn't mean economics isn't important, and it doesn't mean it isn't real, okay? All right, so we have to have a testable hypothesis. This means that, and this is kind of a convoluted thing, but the test needs to have possible outcomes. So I need to have a definitive possible outcome that I could say, if this happens, then I know my hypothesis is wrong, okay? So if I'm testing a medication and I'm saying this medication cures cancer, let's say it cures nose cancer. If I give this medication to a bunch of people that have nose cancer and not a single one has any kind of improvement, in fact, a bunch of them get worse, that is an outcome that says, yeah, your hypothesis was wrong. There is nothing to show that this is something that is curing cancer. Okay, so that's something that we can test. But things that are supernatural, because there are things that we can't control, can't really test them. Okay. Science involves comparison. Of two or more things. My family makes fun of me because every time I watch a TV show where there's a science fair and somebody builds a volcano, I get really angry because building a volcano isn't science. It's not comparing anything. And most people do the whole vinegar and baking soda thing, which looks really cool. I will give you that, but has nothing to do with how a volcano works. So if we're not really comparing things, we're not doing a scientific test. Now, sometimes with science, we might be doing background information and looking into things, but if we're not comparing things, we're not doing a scientific test. Okay, so an experiment, a test, a study is going to be comparing things. What happens when I give this person the medicine for nose cancer? What happens when I don't give this person the medicine for nose cancer? Okay. let's see what's next. Okay, what do we do with the information that we gain? Sometimes we take that information and we say, this supports our hypothesis. So maybe we just have a little bit of gaining of knowledge. When we gather a lot of information, we might do a couple of different things. So a lot of studies together, we might make a law. So we've talked about the law of conservation of mass or matter, kind of use those terms interchangeably. So matter means we don't create or destroy atoms. Mass means this is why things don't gain or lose weight. Okay, so laws are observations. They seem to always be true. There are no known exceptions. Okay, so Newton's law of gravity says any two objects that have mass are going to be attracted to one another. Okay. Every time we look at masses, whether we are looking at an apple and Newton with the apple falling on Newton's head, or two planets, or your pencil and your desk, those things are attracted to one another. Now, because the Earth is the biggest thing in the nearest vicinity, most things are more attracted down towards the Earth than they are anywhere else, but there is a slight attraction between all of us and the ceiling. Okay, so those observations seem to always be true, and therefore they are universally accepted. So if I talk to a scientist in Korea, or I talk to a scientist in Argentina, or a scientist in Russia, or one in this building, and I said, is the law of conservation of mass true? They're going to say yes. Nobody's going to be like, well, I don't believe in the law of conservation of mass. Okay, so laws, we have universal agreement on. There is no debate about those. What is more common for us to think about are theories. And I think I'm going to move this over so I'm not writing so low. So notice with the law, all we said is this is what I saw. We said there were two objects, they were attracted to one another, law of gravity. A theory puts these observations together and explains them. Okay. So 200 years ago, nobody had ever seen an atom. We can't really see atoms because they're so small, but we can use techniques to sort of observe them now. But light is way bigger than atoms are. So of course, 200 years ago, nobody had seen an atom. But Dalton came up with what is called the atomic theory. Okay, so his theory combined ideas like the law of conservation of mass and said, well, why is it we have this constant mass, that mass doesn't seem to appear or disappear? There was another observation called the law of definite proportions, which said when I have a chemical compound, I always get the same ratio. And you kind of use that idea. Why would we constantly have that same ratio? Well, for us, it makes sense. We have these little balls that attach to each other. And so, water molecule always has one oxygen and two hydrogens. Dalton was the one who came up with that theory. So he combined 3 or 4 observations about matter together into a theory that explained all of these laws. If we assume that there are atoms, if we assume that we can't destroy them and we can't make them, then we can explain the conservation of mass, the law of definite proportions, the law of multiple proportions. We can explain a lot of things that way. Okay. So the thing with theories, unlike laws, is sometimes there may be scientists who legitimately have questions about this. So there may be legitimate, let's say, questions. Sometimes they are tweaked, which I mean they are changed a little. In order to keep making them work. And we've had to do this with Dalton's law. So Dalton initially said all atoms of the same element have the same mass. Every atom of carbon weighs exactly the same as every other atom of carbon. So thinking back to our packet that we did a week or so ago, why is that not something that we currently hold as being true? What might be some differences between carbon atoms? They might have different isotopes. So we might have one that has 6 neutrons. We might have one that has 7 neutrons. So we've tweaked it. So his original theory, really good explanation for a 5th grader, right? But we understand it to be a little bit more complicated than that. So honestly, your teachers have always been lying to you, because if we gave you the whole big picture as a 5th grader, like, your brain would fry. So we tell you the best story for you at that time, and then your 8th grade teacher says, well, actually it's a little bit different. And then in high school your teacher says, well, actually it's a little bit different. I'm going to do the same thing. I can't give you the whole truth because I don't know the whole truth, because we've been tweaking these things along the way. So another thing, Dalton said we can't change one element into another, and chemically we can't, but is it possible for one element to become another? Yeah, with radiation. So we can turn, like, uranium, if you've seen Oppenheimer, where he's collecting the uranium and the plutonium, what they do is they break that uranium atom up and it becomes things like krypton and strontium. So it becomes smaller atoms. So it is possible. It just, you have to work really hard at it. So it's a little change. Most of the time, when we're doing chemical reactions, we don't change them from one to another. Okay. So a theory, there may be some questions. Sometimes we have to tweak it a little bit. Usually, if it's something that we know about, if it's not something that's newly published theory in the Journal of High-Minded Science or whatever, usually there is overwhelming evidence for it. So what do we mean by overwhelming evidence? For a scientist, this means there have been many studies that these studies have been published in peer-reviewed journals. A journal's a little bit different from a magazine. It's not really a magazine for scientists. So if you go out and you buy People magazine has this target audience, and they want to put in there whatever is going to, like, get them to buy the magazine. And they're going to have advertisers that are going to give them money to help publish the magazine. Okay. Journals don't have advertisers. So the goal is, this is just science and it is completely unbiased, but it is peer reviewed. Now, every discipline science or non-science, has peer-reviewed journals. So have you heard about peer review in your other classes? Some of you, yes. Okay, so in science, the way this works, and it's probably pretty similar in most of them, I might send in my experiment that I did into a publication, and they might say, this isn't interesting, and send it back. Or they might say, okay, we're going to send this out to some reviewers. Now, these reviewers are going to be other people who study the same thing as me. I don't mean like other people who study chemistry. If I'm doing a study on the solid state chemistry of titanium oxide, it's going to be other people who study titanium oxide. So people who know a lot about the specific field that I'm in. And those 5 or 6 people, some of them might say, well, you spelled a lot of things wrong. And I'm going to be like, yeah, spell check doesn't catch everything. Some of them might be like, oh, you forgot the parentheses around this and you forgot the charge on that. And some of them might be like, this doesn't even make sense. You didn't, verify this with a second backup study. You didn't control for this. And so they might say, well, your reviewer says it's no good. Or they might say, if you explain why you didn't verify it, or if you explain how you could verify it, then we'll accept it. And so this whole process may take like 6 months, going back and forth, kind of like going back and forth with your English professor over a paper. You turn in the paper and they say, oh, you got a lot of stuff wrong. You fix it, you take it in, they're like, oh, it looks better, but you got to, do these other things. But there are people there who are not grading just like your grammar. They're like looking at the science itself. Okay. So that's what we mean by peer-reviewed journals. So before it ever gets published for anybody to see, somebody who knows about the topic has looked at it and said, yeah, this looks like good science. And so in order for that to be considered in a theory, we have to have peer-reviewed journals and lots of studies, not just one. It has to be like a whole bunch of people came to the same conclusions, and I draw all of these observations together in order to get this this theory. So is it proof? No, because in science we can't really prove things. We can't consider every possible scenario. I can't look at every single carbon atom. I can't look at every single tree and say this is always 100% going to be true. So what we do is we gather evidence, and that evidence appears in these studies that are peer reviewed. So there's usually a lot of evidence, lots of studies, and usually it's based on multiple researchers. So Dalton used one of the laws that he came up with, but he also came up with, or he was also basing his work on a law that a scientist named Lavoisier came up with. And he was also basing his, I'm sorry, not his law, his theory, on a law that Proust came up with. So there were lots of different people that did the work that ended up in being a part of that theory. Okay, so difference between laws and theories. Okay, next thing. If we look at these studies that are published in these journals, how do we know that this is a good scientific study? So in science, we are doing a comparison. Our comparison is between things that we call the independent variable and the dependent variable. So generally, we are looking for causality. We're looking for one thing causes something else to happen. Now, sometimes we're doing a correlational study, just seeing if they are related. Is there a relationship between the color of your hair and how fast you breathe, or something like that? Not saying that being blonde causes you to breathe faster or slower, not saying that breathing faster or slower changes the color of your hair, but maybe there's a correlation, okay? We're gonna focus on this one here, where we're saying one thing causes the other. So the independent variable is generally our cause. And this is what is determined by the scientist. This is what I'm examining. So in the case of a medication, my independent variable is whether or not I give you this medicine. Or I might say, what is the dose of your medicine? Do I give you 5 milligrams? Do I give you 10 milligrams? Do I give you 20 milligrams? Okay. So I might say, my independent variable is my dose of my medicine. Then my dependent variable is the effect. What happens when I take that medicine? So in chemistry, we might have our independent variable things be things like the temperature. As I change the temperature, what happens to the chemicals? As I wait a certain amount of time, I might have a stopwatch. What happens over a certain amount of time? Okay. Since people are more familiar with things like, oh, we have to test drugs before we send them to market, kind of go back to that as my default example. Okay, so our effect might be things that we are looking at that we want to happen. Did it cure cancer? We might be looking at more than one thing at a time. So it could be multiple things. Okay, so maybe we have some sort of supplement that we want to say, oh, maybe this helps athletes. What is the effect on its heart rate and the recovery time from after you do your exercise to kind of get your heart rate back to normal? And does it help you lose weight? So we might look at 3 things at once. Okay. The independent variable, we want only one at a time. So what I don't want to do is I don't want to give everybody this drug that I think might be good for them, but also give them a supplement of extra iron. You know, take these iron supplement pills and this other supplement both at the same time. Why not? If I find out that all of the people who do this, you know, have really good benefits here, they're have lower heart rates and better recovery time, what do I know? Do I know that my medicine caused it? If I gave them both the medicine and iron supplements? No, because maybe just the iron supplements helped, right? So I've got to be careful about only doing one of those things at a time. Now, what I could do is I could have one study where I gave some people my medicine and some people not. I could have another study where I gave some people iron and some people not. And then I could have another study where I gave some people both and some people not. And then I would have different studies. So that's why I say at a time. And then maybe I put all of these studies together in one publication and talk about them all, but only one at a time. Okay, so the first thing is making sure we only have one independent variable. But remembering that our dependent variables, we might have lots of things we're looking at. These might also include things that we didn't realize were there, which they try to rush in at the end of the commercial. As side effects. So this may cause headaches, death, and or vision. You know, they throw in a bunch of things, and like one of them is always like, and death. So those would also be dependent variables. A lot of times when they're talking about side effects, they also throw in the phrase, these were similar to placebo. What's placebo or placebo? Heard about placebo before? It's what?
It's when nothing is given, but they're told that they're given something.
Right. So when they're not given something, but they're told they're being given something. So in medicine, we call it a sugar pill. So we gave you a pill and we said, this might be our super magical supplement that's really going to help you, or it might be a sugar pill. You don't know. Or if it's something that is intravenous, like they give it to the IV, they might say, there might be medicine in here, or it might just be salt water that we're putting.
They have to say that.
So, and we'll talk later about ethics, but right now we're just kind of talking about the experimental design. Okay, so why do we give them a placebo at all? The one reason is we have to have a comparison, right? We have to be able to compare having the medicine to not having the medicine. Okay, so we want to treat our groups the same except for this one thing. So we can't just say, I gave you the medicine and you're better, because I don't know if you maybe would have gotten better if you didn't have the medicine. So we have to have that. But why not tell them you're getting the medicine versus you not getting the medicine? Have you ever had somebody in your family who has some like quirky thing that they do to like get rid of headaches or help sleep better at night? They're like, I rub lime juice on my temples and that makes my headache go away. Or if you put onions on the soles of your feet, that pulls out the toxins and makes you feel better. So most of the time I hear those things and I'm like, that sounds ridiculous. But people say, I swear it works. I've tried it and I always feel better. So that's what we call the power of suggestion. Sometimes just thinking that we did something different makes us feel better. Okay, so power of suggestion. Knowing that something is supposed to happen changes our perception. I've been given a medicine, I'm supposed to feel differently in some way. Sometimes people will suddenly get stomach aches. Sometimes people will suddenly feel better. I feel like I have more energy. We can do a similar thing. And so that kind of study, if it's something that we have to worry about, because something that we're trying with diets, where you know the medicine comes to people and we say, okay, we want everybody to try a specific diet, and like to say, yeah, it's really working from a. And they may also say, oh, if I put chemicals in my body, I might have side effects. We're giving them. I had a headache stand, but that's medicine. But we're giving them kind of. I had a stomachache or
Okay.
something like that.
So that's a big.
So if we notice
Now,
the
what
same
about from the
kinds of
scientist
things
then?
in both
Does the
groups, whether
scientist
it's what
know
we were hoping to happen
which is
or
more
side
side
effects,
effects?
and we say, oh,
So
it's pretty much the same in the
know what
placebo
each
group, it's probably
saying
not.
it's
So sometimes yes,
probably
sometimes it
just-
kind of depends. People take medicine,
So
they
why
think something's gonna happen. But if I notice it's
Okay,
very
so
different between.
what you do is you do a double-blind
medicine,
study, but
then
the
I can say,
reason
okay,
it might be
probably the effect
is if I have tried 6
All right,
times,
so
this is why we use a placebo, and by golly, those reviewers just have it out for me. I just have to have some really great results to make sure that they can't say that this isn't real. Even if I'm not trying to fake it, I might be like, oh yeah, this looks really good, except for that one person, but that's probably an outlier, so I'm just not gonna include them in the case because, you know, that's not important. And boy, this looks a lot better, you know, if I really think about this group and, you know, ignore this other thing. And so you have to make those decisions as a scientist, but if you already know what results you want, you're gonna kind of like make the results lean in that direction. So sometimes we do a double-blind study. Now, in some cases, it's easier for there to be a double-blind than in others. So if I'm like telling different people to have a different diet, it may be really hard to not know what diet you're following if I'm watching you eating. But if I am doing something in a sugar pill, then I might say, okay, I'm going to give a capsule that looks exactly the same to everybody. How will the results are? So if you've ever been in the hospital and they've given you like the bracelet and they've taken blood and they put like stickers on things and they got stickers going everywhere, they have these barcodes that have numbers, right? They basically do the same thing in a scientific study. Everything's done on a barcode, and what the scientist sees is the barcodes, or the people who are working with the patient see like the barcodes. So they don't know from one patient to the next what they're giving. But what the scientist receives is not Susie said this. The scientist receives this was the responses and this was the information attached to real versus placebo. So it helps to prevent the scientist from, you know, making those shady judgments. In things like physics and chemistry, that tends to be less done because obviously your subjects don't have brains. Your chemicals aren't going to be like, yeah, I think something's happening to me this time. So that's less common, but in psychological and medical studies, those kinds of things get done. Okay. So these are some of the things that we can kind of do to make sure that we are avoiding our human bias. Now, at another date in a few weeks, we will talk about some of the ethics of this. One article I read that I kind of want to throw out there was they were talking about the idea of doing a placebo surgery. We really wanted to make sure that brain surgery was working. We would do brain surgery on some patients, and on other patients, we would cut open their brains but not do anything, and then compare the results. So would that be ethical, do you think, to cut into somebody's brain but not actually give them surgery and say, well, we might have done something, might not. So you think it's too high risk, other people might go, well, but then we know the results more, as long as like it's basically a safe surgery, so. And that's where it becomes an ethical question that like, not everybody's gonna agree on. Okay, so we'll talk about that in a couple weeks. Okay, so ultimately what I want to be able to do, oh, I forgot to move this over. Ultimately, what I want to be able to do is take not scientific journals, because most of us don't go and browse scientific journals daily, but take what we know about a good scientific study and look at what we might be consuming in our media intake and be able to evaluate from those, is this something that sounds reasonable? Is it not reasonable? Does this come from a well-designed study? Not a well-designed study. There was one more thing I wanted to put on here. Okay, for credibility. So this isn't under avoiding bias, but we want repetition. So if I cure one person with nose cancer with my medicine, then you might be like, yeah, that sounds reasonable. But you might also be like, well, how do we know that they weren't going to get better anyway? But if I cure 100 people, then you might be like, well, yeah, that sounds like that's something. And if I cure 1,000 people, you'd be like, yeah, definitely this ought to be on the market, right? So the more times we do an experiment, the more it is credible. So this might be multiple trials. So if you ever did science fair, you probably had a teacher say, do at least 3 trials, test this at least 3 times, just so you could show it works over and over again. If we're doing something that involves people or animals instead of trials, what we do is subjects. Okay, so the subject is the person or the animal that we're testing on. So how many is enough? It really depends. If I am doing something in chemistry or physics, it's just chemicals are pretty much going to behave the same way every time. So I'm really just judging my ability to be consistent every time I do the test. So a few trials of getting the same results, that's pretty credible. But when I'm talking about people, there are so many variables that could go into, say, something like your health. It could be your stress level. It could be your genetic background. It could be how old you are. It could be your gender. It could be the environment that you're growing up in. All of those things could impact that. And so in order for it to be credible, we want to have a lot of people. So, my eraser. Generally, we start small and say, is this interesting? Okay. Now, if I'm looking at a medicine, we also might start with first cells. Is the chemical reaction we want to see on the cells working? And then if it works on the cells, we might try it in a living organism, a rat, something like that. Is it doing the thing we want it to do in a living organism, and then move on to people? But we would start with a small group of people. Okay, so we first want to know, is it worth studying? But we also want to know any early signs about safety. Okay, so it seems to be working really well, but I had a couple of people who had heart attacks. Now that could have been random because it was just 2 of them. Is the results that we're getting worth moving it to a larger group? So if I'm looking for something that cures toe fungus, I might be like, if there's a chance this is causing heart attacks, let's just stop here. If this is something that is, extending people's lives by another 10 years, we might say, yeah, I think I'm willing to risk that. So then we might go into a study that might be 300 to 500 people, sometimes a little less, sometimes a little more. In this, we are going to really be looking at side effects. Okay, so here, we want to know, is there a real result, a real relationship, cause and effects between our 2 things we're comparing? And we want to know what are some side effects we should be looking for? Do we need to be looking at potential heart problems with this medication? Before we say this is good enough for everybody, so you might remember hearing about we have these potential vaccines for COVID, but we can't get them out to everybody right away. They need to go through testing, and they talk about fast tracking the testing. So usually this process can take years.
But what they ultimately wanted to get to is this last stage where we've tested on thousands of people, right? And in order to test it on thousands of people, we can't just like give them the medicine and then 2 days later be like, oh, still don't have COVID, it's good, right? So we have to give them time to have had exposure in their natural environment. So that can take longer. So then this is where we say, it's the most definitive.
So it usually takes years to do that.
Often. Yeah. So if we're talking about a drug that is just kind of naturally coming to the market for heart disease or something like that, it's not like a national emergency situation the way COVID was. This process can definitely take years. So you may have heard things about like patents, that drug companies will have a patent on a drug and so they can sell it at a really high price and nobody else can sell the drug, and that can last like 17 years. The reason that it lasts so long is it's really, really expensive and they don't know if they're going to get to here in this early human trials and be like, oh yeah, that's a problem. We're not going to go anywhere with that. All of the money they spend up to that point out the window. So we want to encourage those drug companies to keep pursuing a variety of things so that they can eventually have a good result. So this is the one where we say, yes, I believe this is probably something that's really, really, truly real, is when we have thousands of
So
studies.
that's when it's available. Okay.
That's when they start making it available. And there's like the FDA has to approve and they have to say it's safe and they have to say it's effective. But the FDA is not going to say, yep, this is good to go unless they have done this. If they haven't done a test on thousands of people, it's not getting past the FDA. All right, so Thursday we will be looking at different kinds of pollution and we will be looking at graphs.
Okay.